Hello and welcome to another session of Introduction to Astrophysical Fluids. Previously, we discussed the evolution of the blast wave, which appear in general during a supernova explosion, and we also said that interestingly, this type of blast wave also appears when atom bomb explodes. Okay. Now, in this lecture, we will talk about a bit more formally, using some mathematics, about the structure of the blast wave, what is inside. So starting from the center of explosion directly up to the blast wave front, how different fluid variables change, that we will mostly discuss in this lecture. One simple thing is that we will use some mathematics, some basic concepts. We will be using some basic concepts of dimensional analysis and the self-similar solutions. So some parts or some steps of the mathematics may look like non-evident. However, during this lecture, I will not explain everything in 100% detail. Later I will communicate you some elements of calculation so that these parts can be much more clear. So here, for example, you can see that in the previous discussion we actually found that just by using very simplistic dimensional analysis along with the self-similarity condition, we obtained for the blast wave front that the size of the blast wave, which is given by lambda, and this is an explicit function of time, that should be equal to E t square by rho 1 whole to the power 1 by 5, where E is the energy during the, energy at the initial phase of the explosion. Just when the explosion takes place, E is the energy released, T is the time elapsed, and rho 1 is the density of the environment or the ambient medium. Now V lambda was the velocity of this blast wave front, and that was exactly equal to 2 by 5 E by rho 1 whole to the power 1 by 5 T to the power minus 3 by 5. And we said that the velocity is actually changing with time, decreasing with time, whereas lambda increases with time. But now, in this calculation today, in today's discussion, it will be much more useful if we write this expression in an alternative form, equivalent form, which should be written as V lambda is equal to 2 by 5 lambda by T. Simply if you just write this expression as E by rho 1 whole to the power 1 by 5, then T to the power minus 3 by 5 you just write as T to the power 2 by 5 by T, and then you just extract this whole part over here as your lambda, and this will be then T. Simple. But this form will be very much useful for us. Now in the current discussion today, we try to understand the structure of the blast wave. More precisely, we try to determine the variation of velocity, pressure and density from the center of the explosion to the blast wave surface. That means exactly what is happening to the exploded material. So that is the part which we will study today, and we will be using our previous knowledge of shocks. Now let us first study the whole phenomena in the frame of the explosion. That means where explosion took place. That means it is mostly right. If, for example, if a white dwarf explodes, then you see the whole phenomena being placed on the center of the white dwarf, this type of thing. So in this frame of reference, the shock is moving. So this is not the shock frame. Now in the frame of study which we are now talking, the shock moves radially outward with a velocity v lambda, which is a function of t. Now you can easily see here, so this shock front, okay, and this is actually moving in outward direction with a velocity v lambda, okay. So v lambda is outward, radially outward direction, okay. Now let us designate v2, rho2 and p2 as the fluid variables just inside the shock front, okay. Now that is completely okay. Now we have characterized the medium, but now we have to place ourselves in the rest frame of the shocks, because if you remember, the Rankine-Hugoniot conditions were only valid in the rest frame of the shocks. Then what happens there in the shock frame? How the system is started in the shock frame? Well, when you place yourself on this shock, now you are here, okay, then the shock is at rest for you, okay, and you will see that the ambient, because the shock is actually, expanding outwards radially, okay, with respect to the center of explosion, okay, you with respect to the shock, the ambient would appear to approach the shock with a velocity minus v lambda, as simple as that, okay. So in general, why it is? Because in general, with respect to the center of explosion, okay, the ambient is almost at rest, okay. And that was the story for the ambience. With respect to the shock, what happens, that the medium, the everything which is inside, okay, that had some velocity v2 with respect to the center of explosion, and shock had some velocity v lambda, okay. Now with respect to the shock, the relative velocity of this part will be simply v2 minus v lambda, okay. So with someone who is sitting on the shock will see the whole system as that some material from the ambient would actually stream in the shock, and behind this, okay, some material actually is flowing, okay, and is flowing farther from the shock, that means away of the shock, with a velocity v2 minus v lambda, okay. So then if we just make a comparison with our previous v1 and v2, if you remember, then v1 was the v1 was the velocity just in front of the shock, and v2 was the velocity just behind the shock. So here simply you can say that v lambda minus v lambda is equivalent to v1, and minus v lambda plus v2, which is actually v2 minus v lambda, that is equivalent to v2, okay. Now with this thing we are all set for using Rankine-Hugoniot conditions, okay. Now in blast waves, the velocity is so large with respect to the sound speed of the medium, okay. You can actually do some estimate and you can check, and just you can remember that if you can correctly remember the velocity, okay, the velocity was 10 to the power 4 kilometers per second, and 10 to the power 4 kilometers per second means 10 to the power 7 meters per second. So, well, this is not very far from the relativistic domain. However, for simplicity, here we are taking non-relativistic cases, but we are considering the system to have a very strong shock. That means the Mach number can easily be or reasonably be approximated to be very large as infinity, okay. Then, and this condition is known as a strong shock condition. Strong shock, okay. Now we can use the Rankine-Hugoniot condition for the strong shock. If you remember, we said that even if the Mach number tends to infinity, the density jump, okay, will be simply finite, and it will be given by gamma plus 1 by gamma minus 1, the density jump between the material behind the shock to the material in front of the shock, okay. And just by the continuity equation, you know that rho 2 v2 is equal to rho 1 v1. So rho 2 by rho 1 will be v1 by v2. Now writing the new expressions for v1 and v2, Okay, we can write minus v lambda by v lambda plus v2 is equal to gamma plus 1 by gamma minus 1. If you do the simplification, you will see v2 by v lambda. Okay, so v lambda once again, so if you remember, v lambda is nothing but the velocity of the shock front or the blast wave front with respect to the center of explosion, and v2 is the velocity of the matter which is just inside the shock front with respect to the center of explosion, and that's exactly equal to 2 by gamma plus 1. Now just check. Okay, if your gamma is 5 by 3, that's a very good approximation for monoatomic gases. Okay, so if it is 5 by 3, then 2 by 5 by 3 plus 1, 5 by 3 plus 1, this will be 2 by 8 by 3. Okay, so it will simply be so it will be 6 by 8, so 3 by 4. Okay, it simply says that this will be 3 by 4. So this one has a velocity which is greater than the v2. Okay, that you have to understand always. Okay, that the matter which is just inside the blast wave actually has a less velocity with respect to the velocity of the blast wave itself, I mean blast wave front itself. Okay, now if you remember the ratio of P2 by P1, okay, for again the case where m tends to infinity, you can write, so of course it tends to infinity, it goes to infinity, but now we are taking not infinity but very large, then this ratio, you can just refer to your previous lectures, you can, the ratio becomes simply P2 by P1 almost will be equal to 2 gamma times m1 square by gamma plus 1. Okay, and this m1 squared is the Mach number of the ambient. Okay, and then this is nothing but v lambda square by cs1 square. Okay, because v lambda, so v1 is nothing but minus v lambda, so v1 squared is nothing but v lambda square. Okay, so this ratio is 2 gamma v lambda square by gamma plus 1 cs1 square. Okay, now cs1 square is nothing but gamma p by rho if we are talking about a polytropic gas. Okay, actually we will take it later, we will see the adiabatic simply. Okay, so this gamma, so then p is nothing but p1 by, p1 by rho, sorry, so cs1 square will be equal to gamma p1 by rho 1. Okay, if this is true, then you just put it here and you will see that p2 will be then equal to 2 rho 1 v lambda square by gamma plus 1. So this expression finally gets rid of p1, and this is completely very good because p1 is very small, negligibly small. So something which is negligibly small, p1 is the, pressure of the like the ambient. Okay, this is the pressure of the ambient medium. So if that is small, then actually there is no concrete interest to include this in. Okay, so finally we have something with respect to, so P2 in terms of rho 1, V lambda and gamma. Well, okay, now we follow the Sedok's prescription and we first introduce dimensionless variables. Okay, we are doing this thing because at the end we will try to see that if we, that how much, okay, or how long we can use the self-similarity conditions, okay, in order to analytically treat the whole problem. So finally we will try to solve the equations of dynamics. Okay, there is nothing new. Okay, so if v, which is a function of r and t, rho, p, all are functions of r and t, are the fluid variables inside the blast wave, then one can directly write rho RT is equal to rho 2, which is also a function of R and T, times this dimensionless quantity rho bar, rho tilde. So that means that the rho tilde is constructed just by dividing rho by rho 2. Okay. Similarly, V tilde is also constructed by dividing V by V2, but there is one quantity R by lambda which comes into play, and that will be the first power of R by lambda. Okay, so if you remember what R by lambda is, this is nothing but the xi R, and xi R is a quantity which is a constant over time. If you choose two shells, for example with R and lambda, then this xi R will be constant over time. So if your system is self-similar, then the xi R, anything which is depending on xi R will be will be totally uncoupled or independent of time. Okay, so that is something very important. Okay, and this is a famous trick of writing self-similar solutions, that so just by thinking now, if you just follow this writing, that for P we write P2 R by lambda whole square P tilde. So P tilde basically is constructed by P by P2 and then lambda by R whole square. Okay. Now, why this R by lambda whole square they came? Okay. Though, so for for clarifying this part, I will communicate some steps of calculations, but you can also check over internet or in very good books. For example, one of the books, Clark and Carswell, which I recommended in the reference. Okay, you can go through that. But very roughly speaking, here you can see that if you just try to be, convinced just roughly. So rho has, so again, remember the order of moments of these macroscopic quantities. Rho is the zeroth order moment of velocity. V is the first order moment of velocity. P is the second order moment of velocity. So exactly, the order of moment, if it is m, then there will be a multiplication of R by lambda to the power m. So this is a zeroth order, that's why there is nothing, we can see nothing. So 1 is multiplied. Here this is first order, so R by lambda is multiplied, and here this is second order, so R by lambda square is multiplied. So this is a good trick to remember. Of course, the basic reason which comes, that I will give you in a element of calculation, by which it will be much more clearer. Okay, so if you admit for the time being this type of solutions, where rho tilde, V tilde, P tilde, they are dimensionless quantities, and they are not only that, they are functions of xi R, that I am coming to that point. Okay, so they are dimensionless quantities. Okay, then using Rankine-Hugoniot conditions, we finally can write rho is equal to rho 1 times gamma plus 1 by gamma minus 1 times rho tilde. V we can write as 4 by 5 gamma plus 1 R by T V tilde, and P we can write as 8 rho 1 by 25 times gamma plus 1 R by T whole square P tilde. Okay, so this part I recommend you to check at home. Maybe, I am not sure, but maybe I have also some I can communicate this part of calculation as well, but this is highly recommended that you can do it at home. Okay, you start from this and then you use all these relations over here, and finally you should reach to that. This type of elementary calculations I expect that you can do at home. Okay. Now finally, this is very interesting and important point, that due to self-similarity, now we can expect that this V tilde, rho tilde, P tilde are functions of xi R only. So that if we can if we just we can write the equations of dynamics in terms of these variables, and which are functions of Zaire only. That is that is the best way to check that whether the system dynamics is self-similar in nature or not. Okay. Now, boundary conditions are given as this. Okay. All these three things, all this tilde, they are getting 1 at xi lambda. What is xi lambda? Xi lambda is also 1. So this is, if you remember, xi is r by lambda. So xi lambda is lambda by lambda. This is 1. And according to our definition, if you remember, so what will be, so if we are talking about we are studying this quantity at the blast wave surface, then v will be equal to v2, r will be equal to lambda, so v tilde will be 1. Same thing you can do here, and same thing you can do here. Rho will be simply equal to rho 2, and your I mean, of course, I mean, of course, rho will be not exactly equal to rho 2, but for instance, we can write this. So yeah, so there is something to say. Yeah, no, that's completely okay, because we are coming from the inside, so that's completely okay. Rho will be equal to rho 2, yeah, at the surface when we are just moving to the surface. Okay, so I mean, of course, you know that because this is a shock surface, there is a discontinuity. Okay, so proper limit cannot be achieved like that. So what I was just saying 1 second ago is not a mathematically correct statement. Okay, that means just by using these relations you cannot check this. Okay, but okay, if you put these things, then I mean, in the reverse way, you can check the consistency. Okay, that is the best thing you can do. Okay, now it is also true that the process is very fast. That's why an adiabatic equation of state for the gas or the fluid inside the blast wave, okay, is not a bad assumption. Now we are writing the equations of dynamics of the fluid inside the blast wave. Okay, so spherical symmetry is there, adiabatic equation of state will be there. Okay, and we have this continuity equation. This is the Navier-Stokes equation. Of course, forcing and viscosity are neglected once again for simplicity. Okay, and this is the fancy way of writing that p rho to the power gamma is equal to p rho to the power minus gamma is equal to constant. Okay, so if you use these three things and we write the all these three equations in terms of this tilde quantities, that means dimensionless quantities, not only dimensionless, they are functions of xi. Okay, xi r, then you can write del t, you can replace del t by minus 2 by 5 xi r by t dd xi r, and del r by xi r by r d xi r. This is very easy. This is basic calculations of calculus. Okay, and you please check it carefully. Okay, and if you are stuck, please refer to any simple book of calculus. Okay, with partial derivatives and functions of multiple variables, and partial derivatives, total derivative, this type of thing. Okay, so if you replace this thing, then finally del t, del r, both are now translated to dd xi r. Okay, and that's exactly the method by which one can cross check whether the system is really self-similar or not. Now finally, although these equations look like a bit bulky, but you see this is the continuity equation. Just you don't have to go through each and every part of the equation, but just to check that only we have dd xi r. Okay, dd xi r. here as well we have the differentiations are only with respect to xi r. Okay, and all the quantities are either xi or their functions, that means the tilde type of quantities. The same thing over here, the only thing is like d xi r, and all the quantities variables are tilde variables. Finally, this is true for this one as well. Okay, again dd xi r. So finally we are convinced that this system is reasonably well approximated by self-similarity, but what that gives to the structure of the system? Can we have some interesting information about the structure of the system? Okay, so here we have plotted xi r by xi lambda. Okay, and along y-axis, so along x-axis this is this quantity, along y-axis we have plotted three different things for three different plots. One is p tilde, one is v tilde, one is rho tilde. So you see, so this is done, so this one is done for gamma is equal to 1 by 4. Okay, so which is not a very practical case for astrophysics, however, but this is a very practical case for atom bomb, because this was done for air. Okay, but this type of behavior actually is very much similar for that of a supernova. Now the first thing one can see that the radial variation of velocity is much smoother than that of the pressure and density. Okay, so this one basically changes gradually, whereas pressure and density both, they don't change up to this and suddenly they change very sharply. Okay, not only that, if you just notice this attentively, a very small amount of matter is between this xi r by xi lambda from 0 to 0.5. So the amount of matter very near to the center of explosion is very small. So that means if you think that this is a center of explosion, and just the center of explosion you have almost homogeneous type of matter, spherical shell is like a solid spherical solid sphere type of thing, so, full of fluid, that is not a very good picture. Actually what happens after the explosion, most of the thing, it basically detaches. Okay, gets detached very quickly from the center of explosion and goes to a distance, okay, certain distance, and this part you have very small density. However, the velocity is somehow velocity is somehow reasonable. That is only because the very small amount of matter which is also there, they have a considerable velocity. So in terms of velocity, the change is very gradual. Okay, so this is something we can infer infer for the structure of the blast wave. Okay, so it basically it gets detached like an envelope. Okay, plop, and then it gets off. Okay, so one last thing is that it is true that in our whole analysis we somehow discussed the thing using self-similarity, and we actually saw that this was quite a good approximation. But it is true that, please remember, the self-similarity thing is no longer valid for a system where the explosion finally expands in a medium with considerable pressure. Okay, so if for example some supernova explodes in the neighborhood of some dense much more denser astrophysical medium, okay, then this type of problem cannot be handled using self-similarity. Okay, so that was all about somehow a brief overview of supernova and blast waves, which are nothing but a very good application of shock waves. Okay, Here we also discussed two important concepts of, first of all, dimension analysis, which is very simplified but yet very useful, and another is self-similarity. Okay, although I mean for some tricks of self-similarity I did not go into the detail, because this, I mean, in the scope of this course we cannot do everything, but I will try to give you some elements of material, so that this parts, okay, this I mean the style of writing self-similar solutions gets much more clear. Okay, thank you very much.